Okay, so last time we talked about how to use the product rule to find the derivative of two functions that are multiplying together. Today we're going to talk about the quotient rule, which tells us how to find the derivative of two functions that are dividing together. So we have the quotient of two differentiable functions f and g. The derivative of that is going to be derivative with respect to x of f of x over g of x, a little more complex than the product rule. This is where order does matter. We're going to do the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Because of this minus sign, you have to be careful. Yes, you're going to do the derivatives of both of them times again the other function, but if you don't have them in the right spots because of the minus sign, you are going to have the negative of the correct answer. And the AP test is generally very good at making sure the positive and negative answer shows up. Again, the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. That's our quotient rule. So, let's apply that here. So f of x equals 5x minus 2 over x squared plus 1. And I want to find the derivative. So to do that, we do the derivative of the top. Derivative of 5x minus 2 is just simply 5 times our bottom function minus our top function times the derivative of the bottom. Derivative of x squared plus 1 is just simply 2x. All divided by the bottom squared. So that's the setup of the quotient rule. That's the calculus portion of it. The key is make sure you do the setup correctly. After that, there's now just algebra. We're going to distribute in, FOIL the whole thing, and combine like terms. So I get 5x squared plus 5. 2x times 5 is 10x squared, with the negative is a negative 10x squared. 2x times negative 2 is negative 4x, with a negative becomes a positive 4x. All over x squared plus 1. Squared. So when I combine, 5 minus 10 is a negative 5x squared, plus our 4x, plus 5, all divided by x squared plus 1 squared. That is the derivative of our quotient. There is no need to look at it and see if you can actually factor the top, the negative 5x squared plus 4x plus 5. Generally it doesn't, and even if it did, it wouldn't matter. There is no way it's possible to factor a quadratic to cancel with another quadratic, the x squared plus 1 here. So that's as far as it needs to go. We don't need to worry about anything else for this particular problem. And that's how the quotient rule works. Again, as a review, we do the derivative of the top, which is 5, times the bottom, x squared plus 1, minus our top function, 5x minus 2, times the derivative of the bottom, which is 2x, and we do that all divided by the bottom part squared. That's how the quotient rule works. And that's why it's kind of important to remember the order for the product rule, because it's the exact same order. If you think about the first and the second from the product rule as the top and the bottom for the quotient, it's the same concept. So take a look at this one. We have f of x equals 2x squared plus 4, all divided by negative 3x squared minus 9. So again, quotient rule. Derivative of the top. Derivative of 2x squared plus 4 is 4x. Times our bottom function, negative 3x squared minus 9. Minus our top function, 2x squared plus 4, times the derivative of the bottom, which is a negative 6x. All divided by our bottom function squared. There's the calculus, there's the quotient rule applied. Let's now go ahead and actually distribute and factor in. So 4x times negative 3x squared is a negative 12x cubed. 4x times negative 9 is a negative 36x. Negative 6x times 2x squared is a negative 12x cubed, but with a negative now becomes a positive 12x cubed. Negative 6x times positive 4 is a negative 24x, but with times negative here becomes a positive 24x. And again, all divided by our bottom part squared. And we never really want to square out the bottom. It's very unnecessary. We want to leave it the way it is. If you want, you're more than welcome to. It's just an unnecessary portion of it. When I combine, I notice I have negative 12x cubed and positive 12x cubed. They're going to cancel. Leaving just negative 36 plus 24, which is negative 12x, over the bottom part squared. And there's our answer. Now, if you have a graphing calculator like a TI-89, which will do analytical derivatives for you, you might have a slightly different answer because it's going to actually factor out the 3 from this problem down here, square it out, and see if it cancels and stuff. An unnecessary step. The AP Calc test will not expect you to do that on your own. They're going to leave it the way it is right here. But because the TI-89 graphing calculator is very powerful, it will do all this kind of stuff on its own. For the most part, you'll probably have a TI-84 for the AP Calc test. It can't do analytical derivatives for you. It can only do numerical derivatives. So it could evaluate this derivative at a certain number, which is nice, but it can't tell you the actual derivative as a function. The 89 is more expensive, so if you want to go ahead and buy that, go right ahead. I just don't necessarily recommend it unless you're really pursuing a career in higher mathematics, engineering, architecture, things like that that require actual mathematical processes. If you're just going to do this and then go major in business, don't buy this calculator. Okay, now, for this function, we have f of x equals 3 minus 1 over x plus 5. This is a fraction inside a fraction. We don't want to deal with it the way it is right now. It becomes a much more complex problem. So, to get rid of this fraction right here, I should multiply everything by x, top and bottom. That'll eliminate the fraction inside the fraction. That'll give me this as 3x minus 1 over x squared plus 5x. I now have a normal rational function, so I can go ahead and apply my usual quotient rule to do this problem. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So now that we've done that, we've set up as a rational function, I want you to do the next part on your own. I want you to finish the derivative on your own and get your final answer. So I'm going to pause the video while you work on that, and then you can compare your results with what I have later on. Okay, so here's our final answer for the quotient rule. You should have negative 3x squared plus 2x plus 5 all over the x squared plus 5x squared for your actual answer. And again, the way it worked is as a review. So again, we had 3x minus 1 over x squared plus 5x. We did the derivative of the top, which was 3, times the bottom, x squared plus 5x, minus our top function, 3x minus 1, times the derivative of the bottom, which derivative of x squared is 2x, derivative of 5x is 5, that's why it's 2x plus 5. From there we just distribute, 3 times x squared is 3x squared, 3 times 5x is 15x, and then 3x times 2x is 6x squared, but the negative makes it negative 6x squared. 3x times 5x is positive 15x, but again the negative makes it negative 15x. Negative 1 times 2x is negative 2x, but this negative makes it a positive 2x. And negative 1 times 5 is negative 5, but again this negative makes it positive 5. And then they combine to be that answer. So there you go. That's the quotient rule. It's really not that bad. But like with the product rule, don't assume every single time you have a fraction for your functions that you actually have to use the quotient rule. That's not true. If you have this case right here, notice you have a monomial in the denominator. We don't want to use the quotient rule. That's a horrible idea. We want to divide the mono into each piece. This becomes 1/6 of x squared plus 1/2 of x. This now is a very straightforward polynomial function. So all we're going to do, to find the derivative is bring the exponent in front. 1/6 times 2 is 1/3. The exponent comes in front, so the x goes away, leaving just the 1/2. Very straightforward. You will still get that exact same answer if you use the quotient rule. It's just completely unnecessary. First off, because the denominator is not a function, it's just a constant. And then second, even if it was, it's just a single term. Like for example, even if it looked like this, x squared plus 3x over x, I would still divide it into each piece and make it x plus 3, and do my derivative from there. Much simpler than applying the actual quotient rule. Okay, so that's how the quotient rule works. It's with rational functions. Make sure that it is both separate functions themselves. If it's a fraction, make it normal. Don't make it a complex fraction. If it's a monomial term, just make sure you divide it into each piece and then apply it usually. But if it actually is two separate functions, you must remember derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. That is the proper application of the quotient rule. So I will see you next time. We're going to talk about higher order derivatives.